Hello everyone. Today we are going to discuss about morphological image processing. The word morphology commonly denotes a branch of biology that deals with the form and structure of animals and plants. In image processing, we are borrowing the same term from biology, and we are using this word in the context of mathematical morphology as a tool for processing digital images. So what we are going to study in this particular unit? We will be focusing upon initially the basic concepts or the preliminaries related to mathematical morphology. Then we are going to focus upon standard binary morphological operations, and these operations include erosion operation and dilation operation. Further, these two operations are being extended into more operations known as opening and closing operations, so we will be focusing upon these operations as well. Though there are lots of operations and lots of algorithms under mathematical morphology, we are not going to look at all those operations and algorithms in this unit, but we are restricting ourselves to stick to very basic form of mathematical morphology. Also, the last point that we are going to cover in this particular unit is the hit or miss transformation, right? So let us proceed now with the preliminaries of mathematical morphology. So, morphological operations can be useful for gray level image processing and also for binary image processing. We are going to discuss all those mathematical morphology operations with respect to binary image processing. So let us see first what is binarization. So binarization is the process of converting a grayscale image to a black and white image. I'll repeat, binarization is the process of converting a grayscale image to a black and white image. The most popular operation to perform binarization is known as global thresholding, which is a very simple and popular operation that is being frequently used in image processing. In fact, we have seen this operation earlier. So what we do in this operation, given the input, and the input is the grayscale image, right? So we know the grayscale image is having the intensity values that range from 0 to 255. So this image having the range of intensity values 0 to 255, we are going to convert it into the binary form with only two intensity values, black and white. So what we are going to do is, given the input image, we are going to select the proper threshold, say T, and using this threshold we are going to convert the grayscale image into the binary image, right? So how actually this thresholding works? So see here, let us assume that we are having the grayscale image and each pixel intensity in the grayscale image is given as fx comma y. So this is the intensity at the location x comma y. So if f of x comma y is greater than or equal to threshold t, then the output gx comma y would be equal to 1, that is white. Otherwise, we are going to put the output value for that pixel as 0. So we are converting the grayscale image into the binary form. Now let us see one example. See here, this is our input image, which is grayscale image. Okay, so what we have in this image, we are having some foreground. In the foreground we are having some bright blobs, right? and in the background we are having some uniform or the gray colored background, right? So what we are going to do is we are going to use thresholding to convert this grayscale image into the binary form. So see here in the grayscale image, the intensity values are in the range 0 to 255, right? So looking at this particular image, we may say that the blobs, those are the bright structures in this particular image, those blobs may have the intensity value say may be greater than 180, right? And the background, which is dark gray intensity value, if the intensity is less than 180, then we may say that that is the background. So see here, these are the foreground patterns and this gray colored background is available in this image. So if we pick 180 as the threshold and if we apply our rule that if the intensity value of the pixel is greater than or equal to threshold, that is 180 in our case, then the output is 1, that means white, otherwise the output is black. So applying that rule, we may come up with such kind of a binary image. So here see, the foreground is pure white and the background is pure black, right? So this is what we mean by binarization. I hope the concept is clear. So let us proceed with morphological image processing. So as I stated earlier, what is morphology? The word morphology commonly denotes a branch of biology that deals with the form and structure of animals and plants. So as I stated, we are using the same word in the context of mathematical morphology. Or in other words, morphology is the science of appearance, shape and organization. So what is now mathematical morphology? A tool for extracting image components that are useful in the representation and description of region shape such as boundaries, skeletons, etc. So it is usually used as a tool for extracting some image components. Those are useful in representation and description of region shape like boundaries, skeletons, convex hulls and so on. So let us look at the goals of morphological image processing. Morphology offers a unified and powerful approach to numerous image processing problems. Thus, we can mention here few such goals of morphological image processing. It can be used as pre or post processing of images. So, morphological image processing operations are popularly being used for pre-processing of the images, or many times it can also be utilized as the post-processing operations for images after performing some other kinds of algorithms onto the images. Further, these operations simplify image data. These operations preserve essential shape characteristics, and also those operations can eliminate the noise. So many times for carrying out such kinds of applications, the morphological operations can be utilized. These operations also permit the underlying shape to be identified and optimally reconstructed from their distorted, noisy forms. So this is one more goal that we may look at while learning the morphological image processing operations. These operations are based upon the set theory. So the language of mathematical morphology is the set theory, and the objects those are present in an image are described using the sets. So let us proceed with the basic concepts in the set theory and how these concepts are applied or used in mathematical morphology. So when working with images, as I stated, the sets in mathematical morphology represent the objects in the images. So in binary images, the sets are the numbers of the two-dimensional integer space. So let two-dimensional integer space is denoted as z square, where each element of a set is a tuple or a two-dimensional vector representing the xy coordinates of a pixel belonging to the object in an image. Let me elaborate what I mean. See here, suppose we are having this image, right? So image is a two-dimensional image. Is that okay? So let us assume that we are having some object in this image, okay? So let us assume that we are having something like this, right? So this is one object in our image. Now what I said, each element of a set is a tuple representing xy coordinates of the pixel belonging to the object in an image. Meaning, if this is the object, say O1, then this object O1 can be represented as a set. Okay? And what are the elements of this set? The elements of this set are the number of pixels or the size of this set. Size of this set is the number of pixels constituting this object O1. Okay? And each element of this set represents one pixel of the form x comma y. So let us assume that this is the pixel. Okay? And for this pixel, let us assume the x coordinate is say 15 and the y coordinate is say 20. Let us assume, this is simply the assumption. So this pixel that belongs to this particular object is at the location 15 comma 20, right? So that 15 comma 20 is the tuple and that is one of the elements in my set. Okay? Then we may have another point which is next to this particular pixel. So I may say that 15 comma 21, 15 comma 22, all those are the elements, right, in this set that which is describing my object O1, right? So I hope you must have understood now how the objects are being represented in the form of the set. Okay? So let us proceed now with the basic concepts in set theory. So we are having lots of operations, those we can perform using the set theory, right? So let us assume that A is a set in a two-dimensional space z square. Okay, so if small a is given as a tuple with two elements a1 a2 is an element of set A, then we say that this small a belongs to capital A. So this is the set and this is the element, okay, in this particular set, and this element is represented as a two-dimensional tuple a1 a2 or x comma y. Okay, so if a equal to a1 a2 is an element of A, then this small a belongs to capital A. Capital A is a set in two-dimensional space. Further, if A is given as a1 a2 is not an element of A, then the notation to be used is this small a does not belong to this set capital A. Further, set with no element is denoted as the null set or the empty set, and it is denoted as the Greek symbol phi. Okay, so we know all those basics actually. We are simply recollecting back those concepts. Now see here, we are having one set C. C is given as a set. Okay, so how we are going to interpret this set C given like this? We are saying that set C is the set of elements W. Set C is the set of elements W such that W is formed by multiplying each of the two coordinates of all the elements of set D by -1. See here, C is the set of elements W such that W is equal to -D for D, small d, that belongs to capital D. So capital D is the set, okay, and this small d is the element of that particular set. So if we multiply each of the two coordinates of all the elements like D by -1, then we form this W, right? And C comprises of all such elements W. This is what we mean. Say for example, if capital D is the set, and in this capital D I am having few elements like say 2, 3, then 10, 20 and say 15, 80. Okay, so these are three elements in my set capital D. So what I am saying is C comprises of the elements W such that W equal to -D. So I'll be multiplying each element of this small d. So this is my small d. Okay, so each element in this capital D is small d. And what is this small d? Small d is a tuple with two elements, two coordinates. Okay, so what I'll be getting here is W, which is -D. So I'll be having -2, -3, okay, -10, -20 and -15, -80. Right? So C is the elements W such that W equal to -D for D that belongs to capital D. So if this is my capital D, then my C would look like this. I hope you must have understood the concept and how to interpret such kind of a definition of the set. Okay, now let us proceed with few more basics. So what is a subset? The notation that is being used to denote a subset is this. So A is subset of B. A is the subset of B. Okay, what we mean by that subset? So let us see what it means. every element of a set A is also an element of another set B. Every element of a set A is also an element of another set B. So, diagrammatic representation, if I would like to have for this concept of subset, then what I'll say that this is one object, okay, and say this is another object. So, this outer object is A, or this outer set is, this outer set is B, and this inner set is A, okay. So, every element of A is also an element of B, another set B. So, I am saying that A is subset of B, okay. Now, let us proceed with the next concept, union, which is denoted with this notation, union, A union B. So, what we mean by union? It is set of all elements belonging to either A, B or both, where A and B are two sets. So, let us assume that we are having these two objects, say this is set A and this is set B, okay. So, this entire object is my set A and this object is denoted or represented as set B, okay. So, what is A union B? See here, all this shaded region can be denoted as A union B, set of all elements belonging to either A, B or both, okay. Let us proceed with intersection. So, it is denoted with this notation, intersection, A intersection B, and in terms of images, how we can interpret it? A intersection B actually is set of elements belonging to both A and B. So, whichever are the elements, those are common with respect to set A and B, those will form the intersection of these two sets, right. So, see here pictorially, if I am having these two A and B, two sets, two objects, then if I try to find A intersection B, then whichever is the shaded region here, that is giving me the intersection of these two objects A and B. That means this part is common in both A and B, right. If A intersection B is the empty set, then we say that these two sets A and B are mutually exclusive or disjoint, okay. So, let us proceed now with the few more basic terminologies. So, the complement of the set. So, if I am having set A, how I am going to find the complement of that set? So, A complement is given as the set of elements W such that it is not contained in my set A. So, the elements, those are not part of A, form the complement of A. So, let us see the example. Suppose these two objects are given as A and B, okay. So, if I want to find the complement of A, so this is my object A, right. So, the elements, those are not part of A. So, all the outside elements, right, those we may say that it is a set A complement. Set of elements, those are not present or not contained in A, okay, that is A complement. Similarly, we are having the concept of a difference and denoted as A minus B. So, it is the set of elements W such that W belongs to set A and W do not belong to B. I will repeat. What is A minus B? It is the difference. Set of elements that belong to set A but not to set B. Okay, and it can also be represented as A intersection B complement. A intersection B complement. So let us see diagrammatically what is difference operation. So this is my A and this is my B. So the elements, those are present in A but not in B. So see, this shaded region is my difference A minus B. Okay, and this can also be denoted as A intersection B complement. So you can, on your own, you please justify that A minus B is same as A intersection B complement. Okay, so you please try it and find it out whether these two are similar. Okay, so let's proceed now with few more concepts. And the term that we are going to discuss next is translation. So what is translation? So translation is denoted as A subscript Z, right? So Z is the displacement that we are interested in. Okay, so this is the set of elements C such that C is changed as A plus Z for all the elements like A, those belong to my set capital A. So this is translation of set A by point Z, and this point Z is described with two coordinates Z1 and Z2, right? So simply, if we would like to displace the object by some amount, then we may go with this kind of translation operation. So it is the set of elements C such that C is computed as A plus Z, where this A is the element from the original set and Z is a point, right, by which we would like to displace or translate our object or our set. Okay, and this operation would be applied to all A's, that means all the elements in set A. So all the elements in set A are being translated by the point Z. So if these two are my original A and B two objects, let us consider only object A. Okay, so earlier my object was here. Okay, so this point was here. Okay, and what I am trying to do is I am trying to use the translation by this point Z. So Z is given as Z1 and Z2. So this point gets displayed, right, in X orientation by Z1 and in Y orientation by Z2. So in every element I'll be adding Z1 and Z2. So say for example, if the coordinates for this particular pixel are 0, 0 and my Z is say 30, 30, let us assume, then this point would be shifted to 30, 30, 0 plus 30, 0 plus 30. So this point gets shifted to 30, 30. So similarly, all the points, right, all the elements in this particular set will be shifted or will be translated by this point Z given as Z1, Z2. So in respective coordinates, we will be adding Z1 and Z2. That's all. and we will get this translation AZ. Okay. Now the next operation or the next concept in the set theory is reflection, which is denoted as B hat, and B hat is given as W, set of elements W such that W equal to minus B for all B those belong to set B. So for set B, this is my set B, and this set, for this set B or for this object B, we are applying this operation that is called as reflection. So we are getting B hat as the output, and what would be there in the output? All the elements W such that W equal to minus B, W equal to minus B. For all B's, those are present in this set capital B. What does this mean? Suppose this is the point, this is the point, okay. So suppose this is the point like 30 or 30, 100. Suppose the coordinates for this point are 30, 100. Then this point is being changed as minus B. So minus 1 multiplied with this x and y, these are two coordinates of that point, that element. So that point 30, 100, okay, will be now in my output, it would be minus 30 minus 100. Is that okay? So if this is the origin, let us assume this is the origin, this is 30 here, okay, and this is 100. So minus 100 would be towards this and minus 30 would be towards upwards, okay. So this is how each pixel or each point in this set is being converted to form the reflection of the image, okay. So I hope you must have understood the concept. So let us proceed now with the logical operations involving binary pixels and images. So the principal logic operations those are being used in image processing are AND, OR and NOT. NOT is also known as complement operation. So these are the principal or basic logic operations. These operations are functionally complete. These operations are functionally complete. What does this mean? These operations can be used to form any other logic operation. So these are the basic logic operations, and these operations are functionally complete, meaning these operations can be used to form any other logic operation, So combination of these operations can give us another logic operation. So logic operations are performed on a pixel by pixel basis between corresponding pixels in two objects bitwise, right? So logical operations are performed on a pixel by pixel basis between the corresponding pixels. What does this mean? Suppose I am having this one image and this is another image, both are of same size. Okay, so this is image 1 and this is image 2. This is also a binary image and this is also a binary image. So I'll be having some pixels, those are zeros, and some pixels, those are ones. Here also I'll be having some pixels, those are ones, and some pixels, those are zeros. So if I'm performing the operation like I1 and I2, then what will happen? This operation would be performed pixel by pixel. So this is suppose 0, 0 pixel and this is also 0, 0 pixel. Then if 0, 0 is 1 and this 0, 0 is also 1, then 1 and 1, which will give me 1. So this is how the operations are being performed, okay. Now other important logic operation is XOR operation or exclusive OR operation, or some Other operations are also there, like NAND, which is combination of not and. Okay. The logic operations are just a private case for a binary set operations, meaning if we consider the logic operation and it is equivalent to the set operation intersection. If we consider the logic operation OR, then it is equivalent to the set operation union. If we consider the logic operation NOT, it is equivalent to the set operation, that is complement. So logic operations are just a private case for a binary set operations. Okay, so these are the basics. Actually we know all those concepts, but you may think this as a revision. Okay, now see here, we are having a truth table for these three basic logic operations, and, or, and not. So for if I am having two inputs P and Q, so if P and Q both are 0 0, then P and Q would be 0, P or Q would be 0, not P would be 1. 0 1 will provide me ANDing would be 0, ORing would be 1, and not P would be 1. So not is having the, not is the unary operation, you may say. So it can be performed on a single value. Okay, so 1 0, ANDing 0, ORing 1, 1 1, ANDing is 1, ORing is 0. Okay, so I hope now the basic logic operations are clear. Okay, so see here, this is one pictorial view demonstrating the logic of operations. So some of the logic operations between the binary images are being represented here. Okay, so see here, this is the image A. Okay, so in this image A, I am having some pixels, those are white, and some pixels, those are black. So this is a binary image. If I use NOT operation, complement of A, or if I use NOT operation, then not A will be like this. So negation. So black pixel will be converted into white, and white would be converted into black. So this is in image processing, this kind of application, or rather this kind of operation is known as the complement. Now see here, this is my image A and this is my image B. So if I perform the AND operation, okay, then what will happen? If I perform AND operation, then what will happen? See here, whatever is the common set, so this object can be represented as the set of pixels. This is set of pixels, so whichever are the common pixels, those are being shown here. So please understand here that the black color is denoting binary 1 and the white color is denoting binary 0. Black color is denoting binary 1, okay, and white is denoting binary 0, right? So this is AND, this is OR operation, this is OR operation. So all the pixels comprising, so these are the ones, these are the ones. So you may think of like this is one object and this is the background, this is the object in other image, and this is the background. Backgrounds are same. Okay, so whenever these two are of same size, whenever we use A or B, then what will happen? Whatever are those white pixels, or rather the binary ones, right, those are being grouped like this, and we may get something like this, A or B. Similarly, this is XOR operation, A XOR B, okay, and this is NOT AND operation. So see the outputs and try to interpret as per the truth tables of these logical operations. So logical operations can be performed on the binary images, right, because the binary images or the pixels in the binary images are denoted using a single bit 1 or 0, and we can perform the logical operations easily on binary images. With this, we are going to conclude this discussion In the next part of the discussion, we are going to focus upon the morphological operations, basic morphological operations. So thank you.